Hello everyone, my name is Paula and together with my colleagues Ivona and Albert, we're going to present our solution for this fleet sizing, positioning and routing problem. So first we're going to introduce the problem, then we're going to walk you through our solution methods for different parts of the problem. We will propose a methodology for automating the choice of the number of depots, and lastly we will give some recommendations. So in this problem, we had three missions. We want to find the best locations to place a given number of depots. We want to determine an appropriate fleet size for each depot. And we want to find the best routes to serve all customers on any given day. We have some restrictions. The vehicles have a limited capacity, but they can return to the depot to reload at any point. We also have time windows both for the depots and for the customers. So let's move on to the methodology. We broke down this problem into smaller sub-problems that we solve sequentially. So we have two models for strategic decisions. Those are the depot locations and the fleet sizes. And these are decisions that you make once and perhaps revisit every few years. And then we have operational decisions that are required every day to run the operation. And those are the assignment of customers to depots and the routes of the vehicles. We want to mention that this is also the structure we use in the design of our web user interface in AIMMS, with one page for strategic planning and one page for operational planning. And now we will go over our solution methods for each of these problems. So let's start with the depot location. We want to find the locations that yield the lowest overall costs given a number of depots. The choice of these locations has an impact on the cost of the depots, but it will also have an impact on routing costs later on. And the challenge here is to factor in those routing costs without actually solving any routing problem. We propose to formulate this as a p-median problem with two objectives. On the one hand, we minimize the weighted average of the customer to depot distance. And this is a metric that we use as a proxy for the routing costs. And it is weighted because nodes with higher annual demand should count more when choosing locations. And we also minimize depot costs. We need a parameter alpha to control the trade-off between these two terms because they're not directly comparable. One is a distance and one is a cost. So now how do we actually solve this problem? Unfortunately, we have nearly 1,500 customers in total, and that was too many nodes to solve this problem exactly by simply giving our formulation to a MIP solver. So we have used a clustering algorithm called K-method to simplify the problem before we solve it. With this algorithm, we aggregate nodes into clusters based on the distance between them. That leaves us with a p-median problem in the cluster space that is now small enough to solve exactly. Once we have identified a set of clusters or areas where the depots could go, we solve another p-median problem with the original nodes. Where now we only need to consider the zip codes that belong to clusters that we identified in the previous step. Lastly, we have here some results for the depot location model. First, we selected a value for parameter alpha. So on the graph on the left, you're looking at the impact of alpha on the two different goals that we defined for different numbers of depots. Alpha equals 0 means we only minimize depot costs, and alpha equals 1 means we only minimize the distance between customers and depots. We chose alpha 0.9 because, as you can see, it leads to a significant reduction in depot costs with respect to alpha equals 1. And we only have to pay a very small price in terms of the increase in the other metric, that is the average distance between customers and depots. Lastly, we explore different numbers of clusters for the clustering part of the model. And we decided that 500 was a good compromise between solution quality and the time to run the model. So now let's move on to fleet sizing. We want to assign vehicles to depots in a way that we minimize vehicle costs while ensuring we're able to serve the demand of every day in 2018 and 2019, but without looking at 2019 data at all to make decisions. Now, we could solve 365 routing problems in 2018 to find the maximum number of vehicles that we ever need, but that would be computationally prohibitive, and there's also no guarantee that the solution would work for 2019. The demand in 2019 could be higher. So we propose to determine the fleet size by looking at the number of vehicles that are needed on a set of simulated days. So instead of using 2018 data directly, we sample from distributions that we inferred from the data to generate new demand instances. And the benefit of doing this is that it allows us to adjust the demand level of these instances by tweaking the parameters of those distributions. And this means that we can effectively simulate days that represent a worst case scenario and obtain the vehicle requirements from there. And that's the first step in our fleet sizing model. First, the user is asked to choose between one of these four different demand levels that are based on 2018 data. Then the model will use that to simulate 50 instances. We solve a routing problem for each of those artificial days using a fast version of our routing model that we will show later on. And we store the number of vehicles that we needed each day and for each depot, and we add it to a list. Lastly, we take that list of vehicle requirements, we exclude some extreme values, and we get the highest number of vehicles for each depot. And that is our result, that's our fleet size. So lastly, I'm going to show you some results for the fleet sizing model. So in this graph, you're looking at the performance in 2018 for each of those four demand levels that we mentioned previously. So we can see that if we design the fleet based on the P75 demand in 2018, which is our lowest level, the fleet costs are going to be very low. The downside is that there are a few days in 2018 where we don't have enough vehicles to serve the demand. But if the company using this model could rent extra vehicles for one day on an ad hoc basis, the extra cost associated with this, which is represented in the red bar, would be negligible, and the overall cost would remain the lowest of the four options. So this is a very interesting option. If we go to the other end of the spectrum, we have the maximum demand plus 10%. We added this 10% to protect us against a possible increase in demand in 2019. So it's the absolute worst case scenario. We can see that with this option, we have significantly higher costs, but in return, this option ensures that we can serve the demand with our permanent fleet every day. Results are consistent in 2019. There are also a few days with not enough vehicles with the first two options, but with the last two, we were always covered. So to sum up, we would recommend to go for the P75 if renting extra vehicles is an option. Otherwise, we would recommend to go for the maximum demand plus 10% to be safe. And now my teammate Ivona is going to talk about our models for operational decisions.
Thank you, Paula. So the operational decisions are decisions that are made every day. The first step in these decisions would be assigning customers to depots. The logical step would be to assign each customer to their nearest depot and then end up with a solution like this, where we can see that the number of necessary vehicles is 3. On the other hand, if we take into account the routing effort, which is considering a given number of neighbors for every customer, we can end up with a solution like this, where the number of necessary vehicles is 2. This is done by reassigning this customer from the blue depot, even though that's the closest one, to the red depot. In our case, we managed to lower the cost by $18,000 by only adding a negligible amount of time. This is done by considering 2 neighbors for every customer. The next step is the vehicle routing. The challenge here, like in many routing problems, is the size of the problem, meaning that if we have a large number of customers, then we can't really use an exact method, so we use a heuristic, but for a smaller number of customers, we do use an exact method. I will first describe the exact method. This is the branch and cut method, which is an extension to the branch and bound method done by adding cuts to some of the nodes of the branching tree. The first step is solving the LP problem, then running a separation procedure to generate a valid inequality that is valid for the IP problem, but violated by a current solution, and then cutting off the solution and making the feasible region smaller. The valid inequalities that are used in our problem are the software elimination constraints. Now, if we have a look at a vehicle routing problem and this type of solution, the question is, how do we catch these software elimination constraints? We can remove the depot and all of the edges that are connected to it and just observe what we have left. If all we have left are open paths, then we can conclude that the current solution satisfies the software elimination constraints. On the other hand, if we have a solution like this, and again, we remove the depot and all of the edges connected to it, if we have at least one closed path, then now we can conclude that the current solution violates a software elimination constraint. The challenge here is finding a separation procedure that will efficiently catch these violations. The first step here is taking an edge of a given weight. And by weight, we mean when we're talking about the current solution. If we pick this edge, then we want to shrink it. The shrinking is done by creating a new node and removing the two previous nodes. Then every edge, every node that was connected to the previous nodes is now connected to the new node that we just created. At the same time, we're keeping record and keeping track of the new nodes that are created and all the nodes that were eliminated. And we call the eliminated nodes the predecessors of the new nodes that are created. We will continue this procedure until we eventually end up with a solution like this, where we have two nodes and two opposing edges whose sum adds up to greater than 1. In this case, we will feed all of the predecessors of these two nodes into our subtour elimination constraints. If we have two predecessors, then we use the classic subtour elimination constraints, but for bigger subtours, we use the more sophisticated lifted subtour elimination inequalities. At one point, that procedure is going to get too complicated to use on bigger instances. So then we use the heuristic. The first step in our heuristic is the savings heuristic. We first assume that we have as many vehicles as we have customers. Then we will create our savings list. This is done by merging routes 2 by 2, calculating the savings, and then going down the list, trying to merge the routes while respecting all of the restrictions, and then ending up with a solution. The normal savings function, or the classic savings function that I just showed before, is only the first part of our savings function. In our case, we have an additional complication where every vehicle is allowed to go back to the depot, reload, and then perform another route. In order to take that into account, we use something that we call the packing effort, which is adding penalties to parts of the planning horizon. These busy times of the planning horizon are found by taking a route, moving it across the horizon, and then finding overlaps. By overlaps, we mean that we have two routes where they are happening at the same time. So it's physically impossible for the same vehicle to visit them. And we will add a penalty there. What ideally we want is the second case here, where we have two routes that are not overlapping and the same vehicle can complete both of them. On the other hand, if we have a case like here, where we have two routes that are overlapping by a large amount of time, then we don't add a penalty because it does make sense for two different vehicles to visit both of them. On top of all of this, we also do improvements on our current routes. The intra-route improvements are solving the TSP with time windows inside the routes themselves to obtain the optimal solution, and then node exchange heuristics, where we swap two customers from two different tours and then check the solution again. The last step is what we call the route packing. By packing, we mean assigning routes to vehicles. First, we will sort our routes and then go down the list one by one, packing our routes into vehicles. When eventually we can't fit a route inside the same vehicle, we start a new vehicle. If we can't fit a route inside our current vehicle, we will also swap and turn the routes inside the vehicle in order to try and fit more routes inside that vehicle. This procedure will stop when we run out of items on our list. If we look at the results, and if we specifically compare our branch and cut method to the Cplex default in AIMMS, on the right-hand side, we can see that when it comes to the gap, both methods perform similarly. But when it comes to the memory use, our method performs better. If we compare our heuristic to our exact method, the results are very much expected, meaning that the heuristic runs a lot faster compared to the exact method, but our exact method within 20 minutes manages to find a better solution compared to the heuristic for most of the cases. Now the result summary is going to be covered by my colleague Albert.
Thanks, Ivona. We begin by analyzing our methodology, paying special attention to the trade-off between computational time and solution quality. For it, we consider several instances between 2 and 8 depots and took averages. If we apply our full methodology, we obtain a solution after 26 minutes. Note that most of the time is spent in the routings. In some cases, though, we might be interested in obtaining a solution quicker. That's why we also developed the fast solution methodology, which essentially simplifies the routes to consider only the heuristics and assigning the customers to their closest depot, and reduces the number of simulated days needed to determine the fleet size. This greatly reduces the computational time to 1.5 minutes. However, this comes at a cost, as we see an increase of $80 in the average daily costs. Therefore, we recommend using the high-quality solution methodology in decision-making and the fast solution methodology for sensitivity analysis. Let's now have a look at how the costs change as we change the number of depots. In this plot, we've represented the total costs and its components. Observe that fleet and depot costs don't have a year next to them. This is by design, as we took those decisions looking only at 2018 data and checked for robustness with 2019 data. We conclude that routing costs contribute the most to the total costs. There is also a clear trade-off between depot costs and routing and fleet costs. This is expected, as a very low number of depots leads to larger routes and therefore a need for more vehicles. We can also say that one depot is not recommended, as this leads to very high routing costs. The trade-off between depot costs and routing and fleet costs reaches a balance between 2 and 5 depots, meaning those the number of depots with the lowest costs. Among those, 5 depots represents an interesting option, as it is the one with the lowest routing costs, and therefore the lowest carbon emissions. Finally, we conclude that our method is robust, as there is no significant difference in the results between 2018 and 2019. As part of the feedback we received once we submitted our project, we were asked to automate the choice of the number of depots. Having always considered the number of depots as a parameter, we decided that the natural way forward was to do an enumeration. This is of course challenging, as it requires very large computational times. Fortunately, we have the fast solution methodology, which can reduce those greatly. Taking into account the trade-off between depot costs and routing and fleet costs, we implemented the following scheme. Start with 1 and 2 depots and compare the solutions. If there's an improvement, go on to one more depot. Once there is no longer an improvement, it means that the trade-off has reached its balance, and therefore there is no need to compute any further. We obtained that the optimal choice of depot was 5, and it took only 4 minutes to optimize. Let's now wrap up and make some recommendations. We would recommend having at least 2 depots, and if we have to make a more specific choice, we would recommend having 5, because this is the option with low cost that has the lowest carbon emissions. We could recommend designing the fleet to cover P75 demand in 2018 and rent vehicles on peak days, if that's an option. If that's not an option, or the user is risk averse, we would recommend using maximum demand 2018 plus 10% to make sure that all demand can be served. We would also recommend having a demand forecasting tool for better operational planning. And finally, we would recommend including the loading times of the vehicles to make the model more realistic. Thanks for your attention.